Since the early days of rocket science, rocket engines have been used to reliably create the enormous thrust required to break Earth's gravitational bond. During launch, the Space Shuttle main engines blast out enough steam to power 1/3 of the Californian power grid. Imagine harnessing this tremendous energy.
Liftoff.
Over the past 18 years, the California-based company Clean Energy Systems has turned imagination into reality by enabling the same reliable, clean, and powerful principles to be used in everyday energy applications. This energy is produced in a process called oxyfuel combustion, in which fuel is combusted in a pure oxygen environment. The continuous supply of oxygen requires an air separation unit, which separates air into its constituent parts at high purity. Here, the air is cooled to very low temperatures, liquefied, and physically separated in a cryogenic distillation process. Separating out the nitrogen before the combustion process avoids the formation of nitrogen oxides, or NOx, during combustion. Nitrogen oxides are difficult to eliminate air pollutants, typically tied to power production. At the heart of the CES system is CES's proprietary oxyfuel combustor, or gas generator, a rocket engine re-engineered to run continuously. Typically, fuel comes in the form of natural gas or associated gas. However, because the CES gas generator burns fuel in a pure oxygen environment, a large variety of fuels may be combusted, including those which are normally uneconomic, such as CO2-contaminated gas or CO2 EOR, recycled gas. Inside the gas generator, high-pressure water, fuel, and oxygen are delivered through an intricate network of pathways into literally hundreds of small combustors on the face of a platelet stack, the core of CES technology. Each combustor outlet precisely mixes fuel and oxygen stoichiometrically to ensure a clean and complete combustion, leaving no waste in the drive gas. Water is injected into the combustion chamber in several stages to achieve reassociation of combustion byproducts and to quench the drive gas to the required temperature for the equipment downstream. A cooling jacket around the combustor is used for both preheating the water before being injected into the process and for cooling the equipment itself. Taking advantage of another proven aerospace technology, CES repurposed a powerful workhorse engine used for decades in supersonic jets like the F-4 Phantom. With the CES gas generator creating the drive gas, the turbine is stripped down, removing the compression and combustion components, leaving only the high-temperature turbine. Through a volute, the drive gas from the gas generator is channeled through the expander section and power turbine of the engine. Coupled to an electric generator, the adapted oxyfuel turbine boosts the gross power output to 43 megawatts, 3 times the output of the conventional turbine. After exiting the turbine, the residual energy can be used for water desalinization, or, alternatively, the drive gas runs straight through a condenser, which removes the remaining steam. After the turbine or desalinization process, the remaining steam is eventually condensed to water to recycle to the gas generator and is leaving a concentrated CO2 stream. The generated electricity feeds to the grid. After conditioning and compression, the CO2 gets dispatched to a nearby field for enhanced oil recovery. And after cooling, the generated excess water is sent off as commercial product to agriculture or industry. Throughout the process of generating power, water, and CO2, the CES system has zero emissions, making a stackless energy facility possible while providing efficient and attractive solutions for zero emissions power, enhanced oil recovery, and unlocking resource value.